In this lesson, we'll be using slope for 4.01 exit ticket. As a warm-up, we want to try to remember or put down what we remember and know about the slope. So you might remember that the slope is the change of y over the change of x, the difference of y over the difference of x. Also more commonly referred to as rise over run. Sometimes you think of it as a vertical change over a horizontal change. Several ways to refer to rise over run, but rise over run is a very common term that people remember. Some people might remember slope as y equals mx plus b, where m is represented as the slope, as I've written here and here. Parallel lines, of course, have the same slope. Perpendicular lines have opposite reciprocals, so you might remember from Algebra 1 those concepts. You may also remember the difference between positive and negative slopes, right? So for a positive slope, it's climbing up the stairs, so to speak. Negative slopes, it's climbing down the stairs or going down the stairs. Today, what we're going to be looking at is determining whether a triangle is a right triangle using the coordinates of its vertices, and we're going to classify a quadrilateral using its vertices. To do that, we'll be reviewing some shapes, we'll learn about right triangles, practice using slope to determine right triangles, review sides and angles needed in the shapes, and practice using slope to decide on shape types. Then we'll go over a little preview of the exit ticket, and I will illustrate which slides could be most helpful for you in approaching each of the questions on the exit ticket. Let's start by reviewing what this shape actually is. So when you look at this particular shape, what do you think it is? If you selected trapezoid, you would be correct. This is a trapezoid. It has one pair of parallel sides and another pair of non-parallel sides. And although they don't intersect each other in the current shape that it's in, if you were to extend the sides of the trapezoid outward, like so, you would end up with intersecting lines, which means that those sides opposite in that particular diagram are not parallel. The only sides that would be are the bases of the trapezoid, which are here and here. What about this shape? The best description of this shape is that it's a parallelogram. The reason why that's the case is because if you said rhombus, you also have to justify that all four sides are congruent, and we don't know anything about the actual lengths of all four sides. We also can see that there are two pairs, not one pair, two pairs of parallel sides, opposite parallel sides. So that's why this shape is an example of a parallelogram. In the final shape, we have a right triangle. For the right triangle, what gives that away is the right angle, of course. It's a triangle with a right angle, which makes it a right triangle. Speaking of right triangles, we're going to ultimately try to prove or classify that a triangle in the coordinate plane is a right triangle. But in order to do that, we're going to utilize what we refer to as the perpendicular lines theorem. Specifically, we want to show that one side is perpendicular to another side. So in the case of the diagram to the right, we would want to show that the side here, the leg A and the leg B, are in fact perpendicular to each other. To do that, and why we would do that, is so that we can have a single right angle in the triangle, which classifies it then as a right triangle. That's our ultimate goal. So specifically, how does that relate to slope? Well, a couple ways to think about it is, number one, if you can determine the slope of each side of the triangle in question, and you can tell that the product of the slopes equals -1, then that means that the segments are perpendicular. It also means that it forms a right angle as a result, and since it has a right angle, it would be a right triangle. The other way that you can think about having a product of -1 for the slopes, which is referenced right here, is when it talks about showing that the slopes have a product of -1, that means that you're looking for opposite reciprocals. So when we talk about opposite reciprocals, we are looking for two slopes who are actually opposite reciprocals. Can you flip them and change their sign so that they match up? If that happens, you have opposite reciprocals for this particular problem. So in this particular example, we're going to determine whether or not that triangle is a right triangle. I would encourage you to make a note for this particular slide for your exit ticket at the end of the lesson. So to use the slope formula to find the slope of AB, we can use the notation that they've used where we have MAB to represent slope, and we have 7 minus 4 divided by 5 minus 3. So here we end up with 3 divided by 2. So we have a slope of 3 over 2. Furthermore, for BC, we can see that we have 5 minus 7, which is negative 2, divided by 8 minus 5, which is positive 3. So the slope is negative 2/3. For the slope of CA, we have 4 minus 5, which is negative 1, divided by 3 minus 8, which is negative 5. Negative divided by negative is positive, so we have a slope of 1/5. Now we should be able to recognize is a couple things. One, right away we can see that for the two slopes for AB and BC, we have opposite reciprocals. So I want us to take a moment and identify that these two slopes provide us opposite reciprocals. Because they provide us opposite reciprocals, we can then conclude that the angle B, which is where the sides are located, intersecting each other, is indeed going to be a right angle. Now, you can also see this because if you take the two slopes and you multiply them together, you have a product of -1. That also verifies that, in fact, these are going to be perpendicular. What that does is it allows us to conclude that angle B is a right angle. I will point out, however, that it is not necessary to actually identify that the slopes are opposite reciprocals and then follow up by showing their products -1. Because by showing or by identifying that they are opposite reciprocals, this automatically guarantees that they are perpendicular to each other. So if you do one or the other, that's efficient. But if you do both of them, you might be doing a little bit extra, just so you know. I just wanted to clarify that here as well. So either or is acceptable, and it's nice to be able to justify why they're opposite reciprocals, which is what this does here, but it's not necessary to actually do both of these. State whether they're opposite reciprocals or not, or you can just show their product as -1. Either or is going to end up with the same exact conclusion, that angle B is a right angle, which ultimately answers the question, is it a right triangle? Yes, it's a right triangle. Maybe take a moment, pause, and see if you can come up with whether or not this triangle is a right triangle. And obviously we want to show or validate that by showing the slopes of all the sides and whether there's any opposite reciprocals. So in this particular case, we should get 0 divided by -4, or +4 rather, I should say, which ultimately ends up being 0 anyway. So we have a slope of 0. Here we have -5 divided by -5, which is +1 for our slope for BC. And then for the final segment CA, we have 2 minus -3. 2 minus -3 is going to be +5, and we're going to divide by a +1. Now, if you didn't see that, that's 2 plus 3 divided by -2 plus 3, because you have minus minus. So you get 5 over +1, which means the slope is just 5. As you can see, for the three slopes that we have, none of them are opposite reciprocals. Since none of them are opposite reciprocals, we can conclude from that the triangle is not a right triangle. Since there's no opposite reciprocals, which means there's no perpendicular segments, which means there's no right angle, which means it's not a right triangle. Now, as far as classifying shapes, specifically quadrilaterals, we can classify them as parallelograms or as trapezoids. And if they're parallelograms, we can also classify them as a rectangle, a square, or a rhombus. So if you want to classify a parallelogram, first and foremost, from a quadrilateral, you have to ultimately show that both pairs of opposite sides are parallel. And to do that, you need to show that they have the same slope. It's very similar for a trapezoid. However, with a trapezoid, you only have one pair of opposite sides that are parallel and another pair that's not. So you'll find that only one pair is going to have the same slope, and the other opposite sides don't have the same slope. If you do show that it's a parallelogram, you can follow up with showing whether it's a rectangle or a rhombus, or in particular, it could even be a square if it happens to have both properties. So if you're showing that it's a rectangle, you must first show that in fact it is a parallelogram, and then if you show that it has 4 right angles, you're then proving that it's a rectangle. If you want to show it's a rhombus, you have to first show it's a parallelogram, and then you have to show ultimately that it is going to have 4 congruent sides, which means 4 sides of equal length. If you can show that it has the properties of a rectangle and a rhombus, you also can verify that it's a square, in fact, as an example. So I would actually recommend that you refer to this as well as a great reference for your exit ticket and anything related to slope, in all honesty, right? Because this kind of outlines the rules for how to classify shapes, which essentially a big part of your exit ticket is about. So going through an example here, what I'm looking at is I want to figure out whether the quadrilateral in the XY plane, the coordinate plane, is a parallelogram. I want to draw your attention first to the segments BC and AD. BC and AD are vertical lines. It's important to note that for vertical lines, the vertical lines have undefined slopes. Now, what that means is if you look at the two lines, they have a vertical change. That means that there's a vertical change in their position from B to C or C to B, A to D or D to A, but there's no horizontal shift whatsoever. So what that implies then is that there's no horizontal shift, meaning there's 0 movement left or right. So you would ultimately be dividing by 0, which is an undefined action in this particular geometry. So therefore we say that the slopes are undefined because they're vertical lines. So what's important to note about that is that if you have two lines that are undefined in their slopes, they are parallel. So we already have one pair of parallel sides that are opposite. So all you have to do now is focus your attention on the other sides. In this case, if you look at the top segment, AB, and by the description to the right, what you can see is that we can travel in a positive vertical change of 3 and a positive horizontal change of 4. This indicates a slope of 3 over 4. Likewise, you can do that again from D to C, a positive change of 3 and a positive horizontal change of 4. Vertical being the 3, horizontal being the 4. So both of those sides or segments of the quadrilateral have the exact same slope. So we've now shown that there's two pairs of opposite sides that are going to have the same slope, which means that they're parallel. And that is the definition of what a parallelogram is. So this is absolutely a parallelogram. Again, this is another slide I would refer you to for your exit ticket if you are tasked with determining whether a particular quadrilateral actually is going to be a parallelogram. This demonstrates how I might use the particular graph at hand or the ordered pairs at hand to determine that. And I will point out a tool that you can use in combination with your exit ticket that can allow you to visualize your actual coordinates using the Desmos graphing calculator. So here's another example that I would certainly again refer to your exit ticket as a tip for how to better approach the final question on your assignment. Here we want to classify whether it's a rectangle. Before we do that, we must first determine whether or not it actually is going to be a parallelogram. So we have to find the slope of AB, BC, CD, and DA. So for AB, what I can do is I can go ahead and take 1 minus 3 divided by, in this case, the negative 3 minus negative 1. Now negative 3 minus negative 1, of course, is negative 3 plus 1. So here I get negative 2 in the numerator and negative 2 in the denominator, so I get a positive slope of 1. For BC, I end up getting 3 minus 0 divided by negative 1 minus 2. So there I have 3 over negative 3, which is a negative 1 for my slope. For CD, I would have 0 minus negative 2 divided by 2 minus 0. And this is going to get me positive 2 divided by positive 2, which equals, again, a slope of 1. And then lastly, I have negative 2 minus 1 divided by 0 minus negative 3. That's going to equal negative 3 divided by positive 3, which equals negative 1. Highlighting these two in green shows that they are the exact same slope. This indicates that for these two, they are parallel, particularly the segments in question, AB and CD. Highlighting this in orange here, we can see that these two are the same. So what that indicates is that these two are also parallel. So what I'm doing here on the far right is I'm showing that the two segments, the opposite sides, have the same slope. They're parallel to each other. That's the definition of a parallelogram. So this work over here verifies that it actually is a parallelogram first and foremost. You always want to do that first. Then what you should recognize, and I'll do this kind of using this kind of green color here, these two are going to form right angles. The reason's because you have opposite reciprocals. Or another way to think about it is the product of 1 and negative 1 is negative 1. So you have right angles right there, or a right angle right there. You have a right angle right here. You have a right angle with these two. And you even have a right angle when you look at the first and the last, which you have to compare. Because their slopes products are negative 1 for each of those that I paired up, there are 4 right angles in the diagram. This indicates that this is indeed a rectangle as well. So what makes it a rectangle is that we have 2 pairs of parallel sides, which I demonstrate on the right, and we have the 4 right angles as well. So yes, it's a rectangle. You have to make sure that you have 4 right angles. That's very, very crucial, by the way. As a tip, please make sure you recognize you have to have 4 right angles when you're looking for this. So I point that out because on your exit ticket, before I get to that, I'll just refer that I talked about this briefly. And with this particular diagram here, just please keep in mind the fact that with the Desmos Graphing Calculator, you can use this as a tool to show the graphs of coordinates that are provided to you. And I have a second video that I've put on the playlist directly after this that you can watch that illustrates this if you need extra assistance. I do the first 2 examples, so you can try the third one yourself if you'd like, and it will allow you to visualize what you're actually seeing. So with that being said, on the exit ticket, I referred to in this video where I would go to for each of the particular questions to help you better understand how to answer those questions. For the first one, you can see you're classifying it as whether it's a parallelogram or a trapezoid or maybe neither of those. And you're also going all the way. You're kind of showing whether or not it's a rectangle after it's a parallelogram, if it is, or if it's just, in this case, a parallelogram but not a rectangle, or is it just a trapezoid? Then you have your middle one where you're classifying it as whether it's a right triangle or not. And then your last one, you're classifying it as whether it's a rectangle or otherwise not, which the very last example I would refer you to assist you with that particular question. This is going to represent lesson 4.01 over slope.